Good morning, students. We learned in the last class about data transfer instructions. And here in this class, we discuss about data manipulation instructions. The data manipulation, there are three types of data manipulation instructions: arithmetic instructions, logical and bit manipulation instructions, and shift instructions. Okay, so here the first type of data manipulation, we know that data manipulation instructions are used to perform some operations on the data, okay, to manipulate data. Okay, we perform some operations on the data. So for performing operations on the data, we use data manipulation instructions. There are arithmetic operations, okay, that we need to perform on the data. And some cases we perform logical operations on the data and shift operations. So based on the different operations performed on the data, the manipulation instructions are classified, okay, into three. So first is arithmetic instructions. So these are all the arithmetic instructions. Yes, first one is increment. The mnemonic used is INC. Okay, INC is the mnemonic used to increment the data in the registers. So here arithmetic operations are performed on the data in the registers. Okay, so when there is a binary data in the register, to increment or decrement the data, we use the operations. Okay, increment. Increment is adding 1 to the available data. Okay, incrementing it by 1 or adding 1 to the data. Decrementing is subtracting 1 from the data. Okay, so that it gets decremented by 1. Okay, if suppose the instruction given as INC R1, okay, the register R1, and if R1 has the data 0011, okay, it is 3, right? When this instruction is written, it take the content of register R1, okay, this is there in register R1, and it is incremented by 1. When you add 1 to this, 0011 plus 1, correct? Okay, when you add 101010, okay, so this is 0011 is 3. When you increment 1, you get 4. Okay, same way when you decrement, okay, when you perform decrement operation, it subtract 1. What this the mnemonic used is DEC R1. Okay, when this instruction is written, okay, what is R1? 0011. And when decremented 0011, we need to perform -1. How the subtraction is performed? It is 0001, right? Okay, in 4 bits, this one is represented this way. And we need to find the complement, 2's complement. Okay, for subtraction, the subtrahend need to be 2's complemented and added to the first number, correct? Okay, so we find the 2's complement. 2's complement is 1110, and when you add 1 to this, it is 1111. Okay, 4 ones. Okay, when you add 111, it is 101110. Okay, this is discarded. 0010, it is 2. So 3 minus 1 is 2. Correct? This way we perform decrement operation. When added 1, when the data is 3, when incremented, it becomes 4. And it is 3, data is 3. When decremented, okay, decrementing is subtracting 1 from the data. Okay, subtraction is implemented using, by performing complement, 2's complement and addition. Okay, finding the 2's complement of the data and adding it to the minuend. Okay, this way decrement is performed. And we need to note here that when the register has all ones, okay, so this is the data in R1. Okay, if register R1 has data, with all the binary bits is 1. When one is added to this number, what would be the result? 0, 1, 0, 1, 0, and 0. Okay, this is discarded. So the result is 0. Correct? Okay, it is a 4-bit register that is holding 4 bits. So we will consider only this 4 bits and the carry is discarded. So when all the digits of all the bits of the number, okay, in the register is 1 and 1 is added to this, when incremented, it results 0. Okay, we get 0 as the result. And same way, when the bits are 0, okay, when all the bits of the number given in the register is 0, and when subtracted, when we subtract 1 from this generates all ones. Okay, how we subtract? It is 0, 0. You need to find the 2's complement. When the 2's complement of 1 is, okay, the number is 0, 0, 0, 1. The subtrahend here is 0, 0, 0, 1. When you find the 2's complement, it is 1, 1, 1, 1. Okay, when that is added, when we add that, we get all ones. Okay, so this is increment and decrement operations. And the familiar 4 operations, we have learned about this: addition, subtraction, multiplication, the simple addition, subtraction, multiplication, and division. Okay, this is implemented with there are micro operations involved in this to complete these operations. And the next operation is the mnemonics are ADD for addition, SUB for subtraction, MUL for multiplication, and DIV for division. Okay, and the other 2 operations in addition and subtraction is add with carry and subtract with borrow. Okay, so addition, for instead of 2 bits, we will have the carry. Okay, that comes from the previous computation. It comes as a result of the previous computation. Okay, that carry is also added to this. Okay, the other bits. So this kind of addition, okay, this type of addition we call add with carry. It is the mnemonic used is different here, ADDC. It is for addition, okay, with carry. And subtraction with borrow. Okay, same way, the borrow from the previous computation is propagated to the next computation. So this case we call this is subtract with borrow, and the mnemonic used is SUBB. Okay, addition with carry and subtraction with borrow. And the other arithmetic instruction is negate. This negate is finding the 2's complement. Okay, it is even for subtraction. Okay, subtraction is implemented generally with finding 2's complement and addition. So this is included as one of the arithmetic operation. Finding the complement, 1's complement, and adding 1. Okay, and addition, they're adding 1 to that gives the 2's complement. This operation, it is written as using NAG, the mnemonic NAG for negate. Okay, negate means finding the 2's complement. So these are all the arithmetic instructions. And the second type of data manipulation instructions are logical and bit manipulation instructions. Okay, we know about these logical instructions. And, correct, and instruction. Okay, the mnemonic is and, that performs and. What is and operation? When the bits are 1, it generates 1, right? The result of the this operation and logical operation would be 1 when the 2 operands are 1, right? Otherwise it is 0. 0, 0 generates 0. And when it is, if one of the bit is 1, okay, if any one bit is 0, it generates 0 only. Okay, 1, 0 generates 0, only this 1, 1 generates 1. Okay, this is AND. Logical operation and OR operation. Okay, OR performs only in when the 2 bits are 0, it generates 0. All the other cases, 0, 1 generates 1, 1, 0 generates 1, and 1, 1 is also 1. Okay, OR operation. And exclusive OR. What is exclusive OR? XOR, when the bits are 0, okay, when both the bits are same, it is 0. When one of the bit is 1, it generates 1. It is called odd function. Okay, when the number of ones in the input is odd, it generates 1. Otherwise, in all the other cases, means when the bits are similar, it generates 0. Okay, this is XOR function. Okay, these are the mainly used logical function. Okay, generally used logical functions are AND, that performs the logical operation AND, okay, on the given data, and OR performs OR operation, okay, and XOR. And here the bit manipulation instructions. These bit manipulation instructions are useful for manipulating individual bits, okay, or a group of bits that represent a binary information. So here the bits are considered, okay, each bit of the operand is considered separately and operation is performed. So we call it as bit manipulation instructions. Three-bit manipulation operations are clearing the selected bits. Okay, let's say we have a number, we have a binary number 101110. Okay, here to perform selected bits of this binary number can be cleared using clear operation. Okay, the first bit manipulation operation is clear. This is used to clear the selected bits. Okay, here among this, that's why bit operations consider the each bit of the operand separately. Okay, so we can perform operations on individual bits or a group of bits in the operand using bit manipulation instructions. Okay, so here's this clear operation. It is used to clear the selected bits. If suppose we want to clear these two bits, clearing means, okay, means setting the values of the bits as 0, that is clearing. Okay, clearing this content of the, if suppose this is R1, okay, register R1 has this value. Clearing the register means setting the values, all the bits as 0. Okay, when all the bits of this register are set to 0, it is cleared. Okay, that is clear operation. And here using this bit manipulation, as bit manipulation operations considered individual bits of the operand, okay, separately, we can perform operations on individual bits also. So you can select particular bits, okay, few bits of the operand, and we can perform the operations such as clear and set. The three main operations are clear, set, and complement. Clearing is setting the bits to 0, okay, selected bits to 0, and set operation sets the selected bits to 1. If the bits are 0 and you want to set it to 1, okay, that operation is called set. And complement, okay, complement operation is to invert the bits. Okay, if the bit are 0, 0 becomes 1 and 1 becomes 0. 0 is converted to 1 and 1 is converted to 0. Okay, inverting the bits. So these operations can be performed by using the logical operations AND, OR, and exclusive OR. Okay, selective clear, selective set, and selective complement. These operations can be performed using the logical operations AND, OR, and exclusive OR. So let's see how this clear is done. Clearing the selected bits. So if suppose the content of R1 is this 101110, to selectively clear the bits of this register, okay, the bits, okay, if we want to clear the bits here 1 1, okay, the two bits from the least significant position 0 1, this is 2, second bit and third bit. Okay, if you want to clear these two bits, so this is implemented using AND operation. Okay, so what we do, the operand is 101110. Our aim is to clear these two bits. So here we set these bits as 0. Okay, we perform the operation with an operand, another operand, okay, by setting the bits, these bit positions to 0, okay, which we want to clear, and all the other bits we will set all the other bits as 1, and we perform AND operation. So here it is done by ANDing, performing AND operation by setting the bit in the positions where we want to clear. Okay, here in the operand, we said that bits are 0 and all the other bits is 1. And when we perform AND operation, 1 and 0 generates 0. 1 and 1 generates 1 here, and 1, 0 generates 0, and here 1, 0 is 0. 1 and 0 is 0, 1 and 1 is 1. Now, if you observe the result here, the first bit is 1. Here in the result we have 1. Second bit is 1. It is, second bit is 0. It is 0 in the result. And the other two bits, the least significant bits, 1 and 0 are, okay, not changed. And only the bit that we wanted to clear, the two bits are cleared. Okay, this way we can selectively clear the bits of an operand using AND operation. And the second operation, setting the selected bits to 1. This is implemented using OR. OR operation is used to perform this. So if we take, if the operand is 1, 0, 0, 1, 1, 0. Okay, let's say this is our operand, okay, in register R1. And when we perform this selective set, okay, we want to set these bits to 1. There are two zeros here. We want to set this to 1. So here this is done by taking an operand, okay, and setting the values of the operand at these positions, okay, where we want to set to 1. Okay, setting that these positions 1, and all the values, all the remaining bits will be 0. Taking this operand and performing OR operation will give us the result. So when we perform OR here, it is 0, and 1 and 0 generates 1, 1, 0 generate 1. So these three bits we got as it is, okay, in the operand. And here 1 and 0 generates 1, 1, 0, okay, 1 or 0, OR operation generates 1. And here this generates 1. So this bit also, okay, we got as it was in the operand, the same. Okay, and 0, 0 are set to 1 now. These two bits are set to 1. And the third operation is complement. This complement is implemented using performing complement on the selected bits of the operand is implemented using exclusive OR. If suppose we take the same number 1, 0, 0, 1, 1, 0, and we want to complement these two bits. Let's say, okay, we want to complement the bits 0 and 1. So our result need to be 1, 0, 1, 0. Instead of 0, 1, we want it to be 1, 0, 1, 0. Okay, so to get this, what we do, we take an operand. Okay, because exclusive OR, any value, any bit x, exclusive OR with 1 generates the complement. Okay, correct? If x is 0, 0 exclusive OR 1, what it generates, it is 1. Okay, and if x is 1, and when you perform exclusive OR with 1, what it generates, it is 0. Okay, because the bits are same here, 1 and 1, 0. So when the input is 0, we get 1 as the result, and when the input is 1, we get 0 as the result. This is what we want to complement. So setting these bits, we take the operand and set, okay, the bit set these positions to 1, and all the other bits is 0, and perform XOR. Okay, when we perform XOR here, 0 and 0 is 0. When the bits are different, it is 1. Okay, and here it is 0 and 1, 0. XOR generates 1. And it is 0 here, 1, 0 is 1. So 1, 0 we got as it is, and this 1, 0 is there. And 0 and 1 are inverted. Okay, these two bits are inverted, and we got 1 and 0 in the result. These two bits are complemented. And the next operation. So we have seen this clearing the bits of the register and complementing, and even setting the selected bit also can be done. Okay, using setting is done using OR operation. Okay, so AND, OR, and XOR. And the next operation, clear carry. Okay, when the carry is a single bit register. So when there is a carry, clear the carry. The instruction used is CLR-C. CLR is to clear the content of the register, And to clear carry, we use CLR C. And set C. This is to set carry. Means the carry bit is 0. We want to set it as 1. So we use the instruction set C. Okay, when it is 1 and we want to clear it, or means clearing means setting it to 0. The instruction used is CLR C. And complement carry. Okay, the carry is 0. We want to complement, or if it is 1, it results to 0, and when it is 0, it results to 1. So to complement, perform this complement on the carry flip-flop, we use the instruction COM-C. Okay, and enable interrupt and disable interrupt. We have learned a little about interrupt, and still in this chapter, we have another topic, okay, about interrupt. We will be learning it in detail. So there we will discuss. This is to enable the interrupt. Okay, when there is an interrupt signal, the flag has to be enabled. Okay, so that is done by this instruction EI, and disable interrupt is done by using instruction DI. Okay, so these are all the logical and bit manipulation instructions. These bit manipulation instructions are specially used to perform specific operations on individual bits. And the next type of data manipulation instructions are shift instructions. The operations that can be performed are logical shift right, logical shift left, arithmetic shift right. The mnemonic used is SHR A for arithmetic shift right, whereas logical shift right, it is SHR. Okay, and arithmetic shift left, SHLA, and rotate right, ROR. Okay, and rotate left, ROL, and rotate right through carry. When carry is included, it is the operation is rotate right through carry. So RORC and ROLC, rotate left through carry. These are all the mnemonics used for performing these shift operations. Okay, so let's see these operations here. Yeah, let's take, let's say the content of the register is 1101. Okay, it is R1. Let's consider a 4-bit register. So when we write SHR R1, when we perform logical shift, what this logical shift does, it is logical shift right. So it moves the bits to right. Okay, so here this is the first leftmost bit, the most significant bit. This is moved right to the next position. Okay, let's 0, 1, 2, 3. So bit at position 3 is moved to second position. So we get this 1 here, and the next bit at second position is moved to position 1, and bit at position 1 is moved to position 0. And we have a bit at 0th position that is discarded. Okay, that is discarded, and this position is filled with 0. Okay, this is replaced with 0. This is performing logical shift right. When we write the instruction SHR, okay, R1. So this performs this, and when it is shift left will shift the bits to left, right? Okay, so 1, the bit at 0th position is shifted to position 1. So at position 1, we will have this. Okay, and the bit at position 1 is shifted to 2, second position, and bit at second position is moved to third position, and this one. Okay, now in the shift left operation, the bit at the leftmost bit is discarded, and here it is replaced with 0. Okay, this is logical shift left. And arithmetic shift right. Okay, it is SHRA. The mnemonic used is SHRA. Okay, this instruction is different from logical shift right and logical shift left in a way that, okay, here we use, so the numbers are considered as signed numbers. Okay, so the sign is retained here. The sign of a number is retained. Okay, that is done no, when you perform shift right. but shifting left in arithmetic operation. Okay, so let's perform shift left first. It is same as logical shift left only. Okay, so SHLA, arithmetic shift left. Okay, we take this number, the initial number, binary number. Okay, and when we perform shift left, because it is shifting from the least significant position, but the sign bit is at the most significant position. When it is moved left, sign bit is changed. Okay, sign bit, the bit at the previous position will will be moved to this position during shift left. So we get, okay, this is moved to this position, and bit at 1. Yeah, what we did here, is it correct? Shift left 1.
No, ma'am.
No, yeah, this is 0, right? Here it's 0 and 1. When we perform shift left, this 1 comes to this position, this is 0. Okay, I wrote it as 1. So here, okay, when we perform arithmetic shift left, it is 1 here, and then 0, then 1. Okay, this 1 is discarded and this is 0. Okay, so arithmetic shift left is same as performing logical shift left, but arithmetic shift right is different. Okay, here this is the bits are moved from left to right, right? Shift right. So here this is our sign bit. Okay, it is retained there in the same position, and now the bits are shifted towards right, including sign bit. So now bit at third position is moved to second position, and the next bit that is at position 2 is moved to the next position. Okay, then bit at 1 is moved to this position, and the least significant one is discarded. Okay, so this is, so here the sign bit is retained. Okay, so this is arithmetic shift right. And the next operation is rotate. Okay, rotate is, the mnemonic used is ROR. All the logical shift operations and arithmetic shift operations. Okay, when we perform these operations, the most significant or the least significant bit is discarded. Okay, so we say there is a loss of information. Okay, we are this particular number at the least significant position during shift right. Okay, it is discarded. We will not have this binary bit in the result. So there is a loss of information. So to avoid that, we use this rotate operations. Okay, so rotate right and rotate left. The bit at the most significant position is, okay, move to the, instead of replacing this particular bit with 0, okay, when we shift right, we replace, no, put 0 at the most significant position. And when we perform shift left, here is 0. Instead of this, the bit from the other end, okay, will be moved to this position. There is no loss of information here. Rotate right, okay, is done this way. This particular bit, okay, at the left position will come here. So let's first shift it right. So bit at third position will come to second position, and bit at second position is to move to position 1, and bit at location 1, position 1 is moved to here, and the bit at the 0th position will not be discarded. Instead, it will be moved to the most significant position. Okay, so we get that one here. Okay, so the result of rotate right, okay, operation on this number is this 1110. All the bits, okay, there are 3 ones and 1 0. Okay, it is there in the result. Whereas after logical shift right, we have 2 ones and 2 zeros. Okay, it is changed. Now rotate left. When we perform shift left on this bit at the 0th position will move to this position, and then next is 0. Then bit at second position moves to third position, and this bit at the third position will not be discarded. It will move to the least significant position. So we get this one here. So if you observe this result, we have 3 ones. and 10 as okay, we have in the actual number. Okay, there is no loss of information here. This is shifting the bits this way. Okay, is called rotate right and rotate left, and rotate through carry. Okay, when carry bit is included, the same operation is performed, but when carry is included, okay, if we write RORC and ROLC, okay, so there is a carry bit. Let's say here is a carry bit that has 1, okay, and the numbers are this. Let's consider the actual number in the register is 1 and then 1101. Okay, this is R1 and this is the carry, and this is register, content of register R1. So now when we perform shift, okay, means rotate right through carry. So this carry bit is also considered here for performing this rotate operation. So this is considered as the leftmost bit. Okay, in the same way how we performed earlier, but this is included here. So when we perform rotate right, this will move to, the carry bit will move to the next position. Okay, so we get, yeah, it is moved to the next position. And then for getting it, to understand it more clear, let's take 0 in the last least significant position. Okay, so here 1, and the next bit is 1 in the register, so that is moved to the next position, and here we have again 1, sorry, so the carry 1 comes to this most significant bit in R register, and next is the most significant bit of R is moved to the second position, from third to second, and the next bit again is moved to first position, and 0, as it is rotate operation, the 0 will come to, okay, in this position. Carry will have 0. This is rotate right through carry. And rotate left. Okay, how is rotate left performed? This 0 at the 0th position will be moved to this position, and again the next 0 and 1, 1, the carry, okay, 1, and this carry bit is moved to least significant. So we have this, we will have this carry here. Okay, this is the result of rotate left through carry. Okay, so these are all the shift instructions. Okay, these are the 3 categories of data manipulation instructions. We have seen these arithmetic instructions. The arithmetic instructions are to perform increment and decrement, and to perform the basic arithmetic operations, addition, subtraction, multiplication and division, and negate. Okay, negators, finding the 2's complement. And we have logical and bit manipulation operations. Bit manipulation operations to perform the operations on individual bits or a group of bits of an operand. Okay, that is implemented using logical operations, and OR and exclusive OR. And we can also, okay, clear or set the bits of the carry flip-flop. For this, we have these 3 instructions: set carry, clear carry, and complement carry. And to enable interrupt and to disable interrupt, we have the instructions EI and DI. Okay, and the shift operations, to shift, to perform logical shift, to perform arithmetic shift, and rotate. The rotate operation is different from logical shift in a way that the most significant bit is it is rotated. It is not discarded during shift left or shift right. The bits at the corners, okay, or bits at the least significant or the most significant bit is generally discarded. But here, to avoid the loss of information, we take it back to the other end. Okay, that way this rotate operation is done. Any doubts in this?